Hello and welcome back to Easy Math with Nick. Today we are on video number, oh, that's not right. We're on video number 18. I'm only wrote 16. And today we are going to do a wind turbine physics C problem. This was on the AP Physics C exam, Form B for, I can't remember what year. I'll probably put it in the comments or the description, but if you're interested, ask me and I'll find it for you. But um, I'm blanking now. I just did this yesterday, but whatever. Today's question, I said plus air resistance there in the parentheses because there's a little bit of that comes into play very slightly. It's not an air resistance problem by any means, but that comes into it toward the end. So by toward the end, I mean really toward the middle. But that's fine. We'll see that when we get there. So let's dive right into it. Just a little note here. As you can imagine, I am a high school student entering my senior year, so I still have school. So I won't be posting too many videos during the school year. I'll still be relatively active, but expect like maybe like a video a month. I know that seems really slow, right? But you have to imagine that I'm in school and have other priorities. So I don't have all the free time I did in the summer to prepare videos like this. So I'm going to try to hit 20 videos before I go to the one a month thing, but the one a month frequency. But I don't know if I think I will be able to because I'm planning on releasing another one this weekend. So that'll be 19 and then just one more within that following week. And then we should hit the 20 count. And then from there on, it'll be one video a month. But I think that's a reasonable pace considering um, my allocation of time. So just with that out of the way, let's begin. Um, Question 3. A wind turbine includes a 3-blade system. It's important. There's 3 blades. So you typically see on wind turbines that rotates about an axis through the end of each blade, as shown in figure 1. Okay, each blade has length L, mass M. Okay, that's nice. Center of mass located at distance L/3 from the axis of rotation. Okay, that's useful. As shown in figure 2. Okay, derive an expression for the rotational inertia of the 3-blade system. The expression in terms of M, L, and physical constants as appropriate. Rotational inertia of each blade about an axis through a center of mass is given by this equation. Okay, so let's think about what we're given here, right? We're not given any linear mass densities, so we can't use calculus here because we're not given that equation that we can find dm over dl and then do all that junk that we did in a prior video. We don't have that here, so we can't just brute force this question. We need to think about it. They give you the rotational inertia of each blade about an axis through its center of mass. Through its center of mass. That's very important. That's why I circled it. Through its center of mass. Not about its end. We want to find about its end, right? Because that is, this turbine includes its 3 blades that rotate about around the end of each blade, right? So we're dealing with rotation around the end of the blade, right? Not around its center. So what is an equation that relates rotation about from an object about its center, rotation of an object about its center, and about some other axis? That's known as the parallel axis theorem. So we saw this in a prior video, might have been 2 videos or 3 videos ago. And I'll write the equation down first. It states that I parallel, I'll do I para equals I center of mass plus md squared, where d is distance from center of mass, where d is distance from center of mass to parallel. I'll just do the symbol for parallel axis. That's like the parallel symbol. You have 2 lines that don't intersect, right? The reason we can use this here is because you have to sort of think in 3 directions here. But if you look at the wind turbine and you think about the axis going, how do I express this? The axis going through its center of mass. Let's look at one blade. Let's look at this blade here. The axis going through its center of mass is going to be something like here, right? If we look at that axis, it's sort of coming out of the page at us, right? And so is the axis at the blade's end here, right? So both axes, I'll indicate them in both axes, are sort of coming out of the page. They're not going to intersect, which is why they're parallel. So they're both coming out of the page right at us. It's hard to show that visually, but it's hard to do that because I'm not a skilled artist by any means. But that is why we can use the parallel axis theorem, and that's why it's called that. If you had any questions about that. So if we use this equation, we can now find the rotational inertia of each blade about an axis around its end as opposed to its center of mass. So we know that we're gonna leave this as I parallel, but we're gonna use that symbol now. Equals what is I center of mass? What's the rotational inertia around the center of mass? Around the center is going to be that 1/18 ml squared. They give you that, right? This was right here. We just brought it down. When is MD? D is the distance from center of mass to the parallel axis. Well, they give you that, right? The center of mass is located distance L/3 from the axis of rotation. So the center of mass is located L/3 from the blade's end, which is where it's rotating, right? Because it says the three-blade system rotates about an axis through the end of each blade, right? So I know I spoke kind of quickly there, but we're L/3 distance from the center of the turbine. So that is what they're telling us there. If we follow through with this calculation, we'll have 1/18 ml squared plus 2/18 ml squared. What I did there, I did some quick math. I had L/3 squared, which is L squared over 9 squared. I'm sorry, 3 squared, which is 9. So L/9 could be L squared over 9 could be rewritten as 2/18 L squared times M, 2/18 ml squared. That's pretty easy there. And then finally, I don't need to baby step. I don't know how do I say it? I don't need to easy through this as well as I'm going. 1/18 plus 2/18 ml squared. Just gonna get you 1/6 because 3/18 is 1/6. There you go. There's your answer. Is what you want to think, right? But you're not done yet. This is they're asking you for the rotational inertia of the three-blade system, right? We're not done. This is just one blade. So we need to multiply this by 3 blades. So this is going to get us 1/2. And finally, yeah, 1/2 ml squared. There you go. That's your final answer. Because that is just for one blade, but we have a 3-blade system. So it's going to be the same for each blade because each blade behaves the same. So that's why we get that as our answer. Okay, let's move on to part B now. While the wind blows, the 3-blade system operates at constant angular speed. Constant, that's very nice. You love to see that word constant, right? Angular speed, omega null equals 2.6 radians per second. The length of one blade is 36 meters. Wow, pretty sizable wind turbine, right? The numerical value of the rotational inertia of a system is I system equals that ungodly number with the correct units there. Calculate the time t it takes for the outer edge of the single blade to complete one revolution. Okay. So we are, let's convert this into words. Let's just convert units here for one thing that they give you. They say 1 revolution, which because we're dealing with angular speed, and what units are angular speed in radians per second. So they're not telling us their angular speed in revolutions per second. They're putting it in radians. So we need to convert revolutions to radians. 1 revolution, as I hope you know, is 2 pi radians. 2 pi radians. So our angular displacement here is 2 pi radians. 2 pi radians. So I'll put delta theta. So we have delta theta, and we know that our angular speed is constant, right? So we can say that omega null equals delta theta over delta t. Because if our angular, we could just say t because we're solving for t and we're starting, not delta t, just say t, make it less confusing. We know that we're dealing with a constant angular speed, right? So the change in angular displacement over time is going to be constant, right? When we look at this equation is valid when we have a constant angular speed. So when we, this makes it very easy, makes it almost trivial to solve for our answer here. So we'll have 2.6 equals 2 pi over t. Multiply t by both sides and divide by 2.6. So do some 2 steps. 2 pi over 2.6 Um, and let me get a calculator super quick. I'll just get my phone. Um, you're not supposed to have your phone during an exam, of course. Don't want to. Ah, I shut my phone off. Of course I did. I'll run and be right back. Okay, so I'm back. I got my calculator. And this gets you t equals 2.42 seconds. Okay, just had to pause it for a second. That's your answer. So the hardest part of this question is just making a unit conversion from revolutions to radians, and that's pretty trivial in my opinion. So this question also confuses you by giving you the inertia of the system, which I think we use later. Or I would hope you use later, because otherwise they just give you information you don't need. But besides that, that was a pretty easy question. Let's move on. Pretty, not easy, but pretty simple question. Easy. I mean, this is easy math with Nick, right? So I guess it's okay to say easy, but whatever. When the wind stops blowing, the angular speed of the system decreases. Okay, this is the air resistance thing I was talking about before, right? So technically, this is an air resistance question, even though they don't ask you directly about it. So they tell you here the angular speed omega of the system while slowing down is given as a function of time t by the equation omega equals omega null e to the power of negative beta sub 0 t. I'm sorry, beta null t, whatever. Or beta sub 0 null, whatever. I can't tell, but is a constant with appropriate units as shown in the graph in figure 3. Okay. Okay, so they give you that graph. Now what did they ask you? They ask in part I, calculate the amount of energy dissipated from t equals 0 when the wind stops blowing until the system comes to rest. So when we're dealing with dissipated energy, typically you would have that as have a positive sign because we're dealing with dissipated energy. So our answer should be positive, even though, well, when you're thinking of energy dissipated, you might be like, oh, that's negative, right? On the actual exam, I don't know if they care either way, but I would have this as your answer as positive here, because negative would imply the negative amount of dissipated energy. That kind of means you gain that. You can interpret that as gaining energy, right? So that could be very confusing. So I wouldn't put it that way. That's the first thought that came into my mind when I saw this question, because I'm thinking, oh wait, energy dissipated. I've seen questions like this before where they ask for energy dissipated, and I always put a positive sign because on my answer, because if the sign was negative, that doesn't really make sense to me. So that's why I bring that up, because I've seen something like this before. So they're asking energy dissipated. So what is so we're only dealing with rotational kinetic energy here, right? There is no, we do not take into account, there is no, I should say, there is no linear kinetic energy, sorry, or translational, however you want to put it, because this object is, the wind turbine's only rotating, right? It's not moving, it's not it's not moving in any other direction. It's hard to explain this. How do I want to mention this? It's not moving up or down, left or right. It is not experiencing any change outside of rotation. It's only rotating. Any change in position other than rotation. So it's not translating. I think that's the best way to say it. It would be funny if the wind turbine all of a sudden started falling down, and then we would have to account for gravitational potential energy as well, but that's not happening. That would be actually pretty dangerous, so thankfully that's not going on, but it would be funny. I don't know why I said it would be funny. That's a pretty offhand comment there, but let's continue. So if we're starting at, what is our starting rotational, angular velocity? It's 2.6, right? They told us that. 2.6 radians per second. And our final angular velocity is going to be 0, because they tell you it comes to rest. So our final equals 0. So our change in kinetic energy, which is the amount of energy dissipated, is going to be just how much rotational kinetic energy we started with. So, because we're going to lose all of that by the time we come to rest. So, that's going to be 1/2 I system, the rotational inertia of the system, and omega I squared. So, that's going to be 1/2 Oh, this is where that comes into play, right? With the rotational inertia of the system. They gave you that in the last part, right? That's where it comes into play. Okay, I knew we would use it somewhere. Um, times 10.6 kilograms meter squared. Weird unit. Oops, went too far down. 2.6 squared. And now, if you work this out, let me use my calculator here. Unfortunately, my actual calculator died. Perfect timing, by the way, so I have to use my horrible phone calculator, which is just atrocious. 10 to the 6 is a million, so I'll just type out a million. Times 2.6 times 2.6. You get that answer. Okay, that is an answer. 2.26 times 10 to the 7 joules. I'm not going to put in kilojoules. You want to go ahead and do that? Have fun. 2.26 up times 10 to the 7 joules. So that is your answer. That's how much energy you're losing by the time this thing comes to rest, which is quite a bit of energy, right? That's not that's larger than you see in many problems. Let me do this on my calculator to make sure I did the scientific notation correctly. And that is what we have there. All right, let's continue. Okay. Oh, wasn't so bad, right? Now I think it picks up in difficulty though. My phone calculator giving me a little bit of an issue. That's why I had to pause there. But derive an expression for the net torque exerted on the system as a function of t as the system slows down. Express your answer in terms of beta sub 0, omega sub 0, ml, and rotational inertia of the system, and physical constants as appropriate. Okay, so they're asking for a net torque exerted on the system. And we have what? We have angular velocity. We have a function for angular velocity. So if we want to get an expression for torque, we need to know two things. We need to know that angular acceleration is the time derivative of angular velocity. And we also need to know that net torque equals the rotational inertia of the system times alpha. So knowing these two facts, we can take the derivative with respect to time of this function you get here, and then plug that, just multiply, bring that down here, multiply by the inertia of the system to get an expression for torque as a function of time. A function for torque involving time. I think it's the more correct way to say that. So let's take the derivative of what we have up here. So we're going to have omega, oops, still erasing. Omega equals omega, no, E, BO2, something like that. Negative bot. Yep, that's right. Okay, good job. Now dw dt, the omega dt, whoops. There's going to be, we do chain rule here. E to negative bot. Okay, so, oh wait, oops, I made a little mistake here. The T doesn't come out. Bozo. Show myself with Bozo. Not very nice to myself. Okay. So we just did chain rule there. Almost incorrectly because we brought a T outside, which is not how that works. But now we have alpha here, which is angular acceleration. Now we have that, and we plug this, what we have on the right here, into an expression that has torque on the left. So we'll get net torque, which is sigma tau, equals, I just multiplied the inertia in there, E sub 0, omega sub 0, e to negative bot. That's not what this is, but it's beta sub 0 t. That's your answer for C part I. Let me do that a little bit better. To careless there. There you go. Okay, so that is how you find the net torque. So all we did was convert. We had a function for angular velocity, and we just converted that to angular acceleration multiplied by inertia, and then you get torque. There you go. That's how we convert between those two. There's another route you could have taken as well. You could have multiplied. You could have realized that if you multiply that function by the inertia, you could have gotten a function for angular momentum, and then you got L equals I system get that as a function for angular momentum. And if you realize that net torque equals the time derivative of angular momentum, you can just take the derivative of this to get your same answer. So it's basically two sides of the same coin here. But if you just thought that if this makes more sense to you, wonderful. But can't see the same answer either way. That's what we had down here. Yes. What's multiplied out front is just swapped order, but that doesn't matter because multiplication doesn't care about order. There's some property I'm forgetting the name of. Whatever. For multiplication, what's it called? Associative property? No, that can't be right. Whatever. This is still your answer, but that's just another way to do the question. Same steps, different order, and different concept if you want to bring angular momentum into it. But I doubt anybody would think of that. So, but I just did because I like to anticipate how my viewers might solve questions differently than me. Okay, so now finally we are almost done. They asked for an expression for angular displacement as a function of t. Okay, okay, you might be thinking, wow, this is really easy. You learned in probably your calculus class that change in position is equal to the integral of the function, the indefinite integral of the velocity function, right? Function for velocity. This is what you see in calculus class. It's nothing too crazy, right? But here we're just rewriting this expression, but with our rotational variance for our kinematic quantities, right? So we're going to have delta theta equals negative t dt, something like this, right? And that's not bad, but we need to not forget our limits. There might be some scenarios where I think, that's where I'm blanking a little bit here, but our limits are still very important here because we need to take into account that we're starting at an angular displacement. We're starting at an angle 0 and going, we're starting at time 0 and we're going to a time t. We need to account for that because otherwise we would get an incorrect answer because we're not, at that point, we're not really obtaining a function. We're just obtaining an antiderivative, which doesn't really apply well to the scenario we have. Doesn't really do it for us. It's hard to explain, but if you look at our expression up here, even if you plug 0 into that, how do I explain this in a way that makes sense? We just need, essentially, just don't forget your limits. I'm trying to explain this in a way that makes intuitive sense, but don't sweat it. Just don't forget your limits here. Your limits when you solve this question are very important. Whereas in some calculus class, I don't think sometimes your limits for these types of questions might not be necessary for whatever reason, but I could be wrong on that. Whatever. Let's continue with the question. So we know to get from angular velocity to angular displacement, we need to integrate, but what are our limits? So we'll have delta theta angular displacement equals t equals 0 to t equals t of, what was our function? We'll bring this down here. I don't know. E to negative bot dt. What was that? For the noise inside. That's scary. Okay. So now if we continue with this, we'll pull out the omega sub 0 e to negative bot dt. And that's an integral, which is on your equation sheet. If you needed to, well, it's not this exact integral, but it was the format in which you have e to the negative, e to the a integral, like e to the a dA or something, e to the x dx, where you have an integral like that, where there's we have e to ax dx. It's going to be the format 1 over a e to the ax plus c, right? That's the format. That's an integral that they give you on your physics equation sheet when you take this exam. So you don't need to you don't even need to recognize this integral and mentally figure out the antiderivative. They give that to you here. So that is on your equation sheet or something very similar to that. I think they use a. The reason why that works is if you took the derivative of this side here. Give me a second. Okay, so yeah, so if you brought that a out because of chain rule, I'm sorry, I had to pause for a second because I heard some weird noises in the other room. If you pull that a out, with chain rule, a times 1 over a is 1, so that gets you back to what you had inside the integral here, so the antiderivative is valid. So that's on your equation sheet. So if we take that integral format and apply it here, we'll have an antiderivative of 1 over beta sub 0 t e to the negative beta sub 0. I'm sorry, negative beta sub 0. I keep doing that where I bring the t out. You don't need the t there. That's silly. Beta sub 0 e to negative beta sub 0 t. And we evaluate that from what? 0 to t. And this will get us our answer. Delta theta equals beta sub 0. Once we evaluate the limits here, it's going to be negative. Make sure to evaluate the limits here, not just disregard the lower limit, as when you're dealing with antiderivative that has e, when you plug in 0 here, you're not just going to get something that is just cancels out to 0, because e to the negative 0 is 1. So whatever you have out front here is still important, because 1 times that is going to be whatever that is. So you can't just neglect that. So don't just neglect your lower limit. It's happened to me before. With a question similar to this, don't do it. Minus 1 over beta sub 0. So we're going to get starting to wear out by the end of this, but we'll persevere and finish it off strong. So if I just rearrange what we have in the parentheses here, I have 1 over beta sub 0 plus, minus 1 over beta sub 0 e b o t. We pull this out of the brackets that are now going to be parentheses because I feel like it. Yeah, let's make this a parenthesis. We can't have that mismatched like that. There you go. We'll have and this is our answer for a function for angular displacement as a function of time. And so this does seem pretty similar, at least to me anyway, to this a similar type of function that we saw in our air resistance videos, where we had e to the negative something, right? So it's sort of that type of like exponential decay type function that we saw in prior videos, because that kind of makes sense here because we're slowing down, right? And we're slowing down in a scenario that logically has air resistance going on. That's what's causing this turbine to slow down. So that's sort of just what's going on in the background of this problem. That never really comes up in the rest of the question. But okay, we do have a part D. Womp womp. Okay. This stinks. Okay. Well, let's do it. I thought we were done. Dang it. Okay. The three-buoy system now replaced with a second three-buoy system, identical to the first, except that the second system now slows down according to the equation. This, pretty similar as before. I'm not going to read it again. Where this stays the same, but that constant within the power there is greater than what we had originally. So, and they show the original one as a dashed line in the graph right there. Okay, so now we need to sketch the angular speed of second wave system as function time t. Normally, what I would suggest here is if we have an equation for angular velocity that's like 2e to negative 3t or something like that, right? Now we're dealing with, now this 3 is going to not become a 3, but now we have a new function. That's 2. 2 stays the same. This is just purely hypothetical, to negative 100t. Because, look, negative 100 is greater than 3. And 100 is greater than 3. Because 100 takes the place of this new b value that they're telling us is greater than the original, right? So this is just a scenario, and 2 stays the same because both of these are equal. obviously, right? They're keeping that the same. So 2 equals 2. Just for proof, just to 2 equals 2, great, right? No, just to show, just to make as clear as possible what I'm doing here. So if we look at these two graphs, what this is going to look like is, the graph is going to approach 0 much, much quicker. Because if we look at this, I use two different colors here, red and blue. If we make like a table for both, if we make a table for red of time and angular velocity, if we plug in 0, angular velocity is 2. If we plug in t equals 1, angular velocity is going to be 2 over e to the 3. And we plug in 10, 2 over e to the 30. Right? It decreases still decently fast, but nothing compared to the second function we have here, right? If we plug in 0, still 2. Okay, we're starting out at the same place, right? But we plug in 1, it's 2 over e to the 100, which is very, very, very small number because e to the 100 is a huge number, right? And we plug in 10, well, that's really small now, right? 2 over e to the 1,000 might as well be 0, right? We're getting very, 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 very close to 0, so we're slowing down much, much quicker, right? So our angular velocity decreases much faster with this new equation here. So if we look at how this is going to change our graph, if we want to sketch the new one is going to maintain a similar curve shape. It's going to still trend down, of course, but it's going to reach 0 much quicker. So it's going to look something like that. I'll do the last part a bit better. There you go. It's going to the turbines in this new second system are going to slow down much quicker. So that is what our graph is going to reflect that with the fact that our angular velocity is going to approach 0 at a faster rate, as seen in the graph there. So ideally, you can see this for yourself if you put both of these graphs into your graphing calculator. But I don't have a graphing calculator in front of me. I only have my phone, which can't do that. So, well, maybe I download an app eventually. But there you go. That I felt like my illustration there was sufficient for illustrative purposes. So that was this question. If I did anything wrong, make sure to correct me in the comments. I think I probably made a slight mistake somewhere, but I don't think I did. The answer key for this is online somewhere. College Board always releases scoring guidelines and stuff. So I haven't looked at that yet, but I can take a look at that whenever. It's video 18 now. It's not 16. So this was video number 18, Easy Math with Nick. I don't know why it says 16. I think that was just a typo, but I carried it over to writing. But thank you for watching. This one was a little longer than I would have liked, but I feel like I explained everything in excruciating detail, which is very helpful. So you can fully understand the process of how I solve this question. So I have nothing else to say. There's a couple parts in this question that seem more difficult than they really are. Like part B, they give you two things you don't need: the length of the blade and the inertia of the system, which you don't need to solve the question. So don't get caught up in all the extra junk that they give you. And focus on what they do give you for part A, right? You don't use calculus, you just use the parallel axis theorem, which might be on the equation sheet, but I don't think it is. Still know it regardless. Might not show up too often, but it's always good to know, right? Part C, part I was pretty simple. Just find the energy dissipated. Part I were taking the hardest part of those questions. We're taking a derivative and integration specifically, respectively. Sorry, and knowing how to convert, how to use integration, derivation to convert between those quantities, from going from angular velocity to angular acceleration, going from angular velocity to angular displacement through integration, right? Not forgetting your limits. That's a big thing, and mistake I've made before, so that's why I kind of harped on it there. With my illustration for part D, it's less of a physics question and more of a math question, right? If we increase the constant in front of t in the exponent there, what's that going to do? That's going to make the graph decrease angular velocity decrease much quicker, which is going to make the graph approach 0 much quicker. So that is shown in our sketch there. And I think that's all I want to cover today. Thank you for watching. Next video should be either on calculus. I think it's going to be a calculus free response question. Been meaning to do another one of those. So look forward to seeing you in that. That'll be up this weekend. Not in not too far from that. So thank you for watching. Again, I think I said that 3 times by now. See you in that next video. I think I also said that again, right? Losing it. This was a good one. See you then.